Hi students. Now let us see S black elements. S black elements can be classified into two groups. They are 1A group elements and 2A group elements. 1A group elements are called as alkali metals. 2A group elements are called as alkaline earth metals. So left side I'm representing alkali metals, right side alkaline earth metals. First physical properties let us see. Atomic size and ionic size of alkali metals is from lithium to cesium increases. So here I have given the order. Lithium is less than sodium, which is less than potassium, which is less than rubidium, which is less than cesium. Even ionic radius also following the same order. Lithium plus to cesium plus to cesium plus that is increasing. Coming to the alkaline earth metals, beryllium to barium atomic radius increases, ionic radius also increasing. Density. Density of Phallic group elements, if you consider, there is no regular change in the density. So lithium is having least density. After that, potassium is having less density than sodium, then rubidium, then cesium. Cesium is having highest density. So here, if you follow the regular trend, after lithium, sodium should come. But here, there is a abrupt increase in the volume of potassium we can see. That is the reason density decreases. Next, second A group elements, if we consider, here the density is calcium is less than magnesium, which is less than beryllium, which is less than strontium, and which is less than barium. So among all these, barium is having highest density. Next, ionization enthalpy values. So lithium to cesium ionization potential values decreases because size of the atom increases. So electropositivity and ionization enthalpy both are inversely proportional in relation, right? So if you see here, lithium to cesium ionization potential values generally decreases. So ionization potential values decreases, electropositivity character increases. Coming to the 2A group elements, beryllium to barium ionization enthalpy values decreasing. Highest is beryllium in second group elements, and lithium has highest in the first A group elements. And next, electropositivity character, if you see in second group elements, so beryllium is less than magnesium, which is less than calcium, then strontium and barium. So here cesium is used in photoelectric cells. Cesium, even rubidium is also sometimes we are using. So mostly cesium is used in photoelectric cells. This is because of its low ionization enthalpy values. Next, reducing character. So reducing character also not following the regular trend. Among 1A group elements, lithium has highest reducing power because it has more negative SRP value. So generally, the elements which are having more negative SRP value are acting as strong reducing agents. So exceptionally here, sodium is having least reducing nature in 1A group elements. In the case of 2A group elements, barium has high reducing property. Beryllium is least, then magnesium, then calcium, then strontium, then barium. Next, hydration enthalpy. So your hydration enthalpy is more in the case of lithium in 1A group elements, then sodium, then potassium, then rubidium, then cesium. Coming to the second A group elements, beryllium plus 2 is having more hydration enthalpy than magnesium. So slowly it is decreasing down the group. So here ionic mobility or conductance is inversely proportional to hydration enthalpy. Means the element which has highest hydration enthalpy having least mobility, least conductivity. In a 1A group elements, if you consider, lithium has least ionic mobility because of its highest hydration enthalpy. In the second group elements also have given here, beryllium 2 plus is having less than magnesium plus 2, then calcium, then strontium, then barium. Next, mobility in electric field. So lithium is more than sodium, then potassium, then rubidium, then cesium. In 2A group elements, Be plus 2, then Mg plus 2, then Ca plus 2, Sr plus 2, Ba plus 2. Melting point order. So melting point is more in the case of lithium in 1A group elements because of its hard nature. And in the case of second group elements, beryllium is having highest melting point. Boiling point are also same following. Lithium is having more in the case of 1A, beryllium is having high in the case of second group elements. Next, complex forming tendency. So generally, the elements whose size is small, they are forming complexes, and charge density is more, they can form complexes. And the elements which are having vacant orbitals, they are also acting as, or they can form the complex compounds. So to form complex compounds, these three conditions are very, very important, right? Now let us see, in the case of 1A group elements, only lithium forms complexes in 1A group. Coming to the second group elements, beryllium and magnesium form the complexes. What type of complexes? Here I have given BeF2 plus 2F minus gives rise to BeF4 2 minus, and the second, third examples also I have given. Next, coming to the flame test. So here 1A group elements, 2A group elements both are giving characteristic color to the flame test. Lithium is crimson red, sodium is golden yellow, potassium is pale violet, rubidium is violet, and cesium is blue in color. Coming to the second A group elements, beryllium, magnesium, they cannot give any color, right, on element test. Means single elements, if you take, they are not giving any color test, right? The reason for this is their ionization enthalpy is high. But calcium, strontium, barium belongs to the second group elements. They can give the characteristic colors. Calcium gives brick red color, strontium gives dark red, barium gives apple green color. Now let us see chemical properties. 1A group elements reactivity, if you see, lithium to cesium reactivity increases. Same in the case of 2A, beryllium to barium reactivity increases. Next, let us see reactions with the hydrogens. When the metals react with hydrogen, they form hydrides. So generally 1A group elements when reacts with hydrogen forms metal hydrides of type MH. So here metal is nothing but sodium, potassium, rubidium, cesium, right? All these are the metals that metal hydrides, whatever are formed, they dissolve in the water and forms their respective hydroxides, which are called as alkalis. Same way, 2A group elements will form MH2 type of hydrides, and these hydrides, whatever magnesium hydride, calcium, strontium, barium hydrides, all these are the second group hydrides. So these hydrides are also formed when beryllium chloride of second group element react with lithium aluminum hydride, which is a strong reducing agent. Also we can get beryllium hydride. So here second group hydrides also dissolves in water, forms MOH taken twice type of the hydroxides. So here calcium hydride is called as hydrolith. Generally this hydrolith is used in the production of hydrogen gas. So the reaction is CaH2 plus H2O gives rise to CaOH taken twice and H2. Next, let us see thermal stability. Thermal stability, if we observe, lithium hydrides to cesium hydrides, if we observe, thermal stability decreases. Lithium hydride is more thermally stable than cesium hydride. Same way, beryllium hydride to barium, its stability decreases. Next, here one more property we can discuss, that is reducing character, which is inversely proportional to transition state. Now here reaction with oxides also let us discuss. So here whatever the 1A group elements and 2A group elements are there, they react with oxygen forms oxides, right? Now alkali metals will form three types of oxides. One is normal oxide, and other one is peroxides, and next superoxides. These three categories we can see. So generally lithium is forming normal oxide, sodium can form sodium, that is peroxides. Along with peroxides, even sodium also can form simple oxide, Na2O also possible for sodium. Okay, Next, let us see superoxides are formed from potassium onwards. Potassium, rubidium, cesium, they can form superoxides, right? And these superoxides are colored in nature, at the same time they are paramagnetic in nature. So most of these compounds paramagnetic. Coming to the alkaline earth metals, beryllium oxide, magnesium oxide, and whatever calcium oxide, strontium oxide, and barium oxides, if we consider, beryllium oxide and magnesium oxide can form simple oxides. So these are called as what? Simple oxides. Whereas calcium, strontium, and barium oxides are called as peroxides. And these peroxides are colored due to lattice defects. At the same time, these compounds are diamagnetic in nature. Superoxides are paramagnetic, whereas peroxides of alkaline earth metals are diamagnetic in nature. Next, basic character, let us see. So generally basic character of the oxides of 1A group elements and 2A group elements both are increasing from top to bottom. Means lithium to cesium in 1A group, beryllium to barium in 2A group, basic character increases. Next, hydrides. In hydrides, so whatever the metal oxides are formed, they dissolve in the water, forms hydroxides. 1A group elements will form MOH type of hydroxides. 2A group elements will form MOH taken twice, 2 type of hydrides. So lithium hydride, sodium hydride, potassium hydride, rubidium, cesium hydroxide. Okay. Next, here second group elements will form beryllium hydroxide, magnesium hydroxide, calcium, strontium, barium. In this order only their basic strength increases. Next, reaction with water. So 1A group elements dissolves in water, forms MOH type of hydroxides. They are called as alkalis. Along with that, hydrogen gas is liberated. The same time, 2A group elements also reacts with water, forms MOH2 type of, that is MOH taken twice, 2 type of hydroxides. Along with that, hydrogen gas is released. But here lithium is less reactive with water, right? Among 1A group elements, lithium is less reactive. Coming to the sodium and potassium, they are highly reactive with water. Easily they can react with water. Rubidium, cesium, if we take reactivity with an explosive reaction, means highly reactive. Down the group reactivity increases, we discussed. Same way, second group elements, if we consider, beryllium is not reacting with the water. Do not react. Magnesium react with hot water only because it is less reactive. Calcium, strontium, barium react with even cold water also. Why? Reactivity increased down the group. Next, nitrites. So 1A group elements, 2A group elements, they forms nitrites. But coming to the 1A group elements, only the element lithium can form nitrites, not all the elements belongs to 1A. So only lithium reacts with nitrogen, form nitrites. That reaction is this. So when lithium is reacting with nitrogen, forms Li3N2 is formed. 2 moles, 6 moles, right? So 2 2s are 4. 2 moles of nitrogen you can take, right? So this Li3N, this is 1 second. So the reaction is lithium reacts with nitrogen, forms Li3N. Okay, so 2 moles here, 6 moles here, right? So this is lithium nitride. Now this lithium nitride dissolves in water, forms lithium hydroxide, and ammonia gas is evolved. But coming to the 2A group elements, all the group 2 elements form M3N2 type of nitrides. Here I have given beryllium nitride, magnesium nitride, are formed easily and they can soluble in the water and forms their respective hydroxides, carboids. So 1A group and 2A group elements will react with carbon and form carboids. So carboids of 1A group elements dissolves in water, forms hydroxides. So beryllium carbide gives beryllium hydroxide, magnesium carbide gives magnesium hydroxide, calcium carbide gives calcium hydroxide. Along with that, we are getting hydrocarbons. In the first case, methane, second case, propane, and the third case, what? Acetylene is formed. Next, second group elements also, they react with carbon forms carbides, and so all are the second group elements I have given here: beryllium, magnesium, calcium. So CaC2 plus 2N2 gives rise to CaNCN taken twice. BaC2 reacts with N2 forms BaCN taken twice. Halides. So here metals when reacts with the halogens form metal halides. That metal halides, right, also formed when hydroxides of metals of 1A group and a 2A group reacts with hydrogen halides. So here metal hydroxide when reacts with HX forms MX, that is nothing but what? Metal hydride of 1A group element or 2A group element, anything you can take. MX is there, so it is 1A group element. In the case of 2A group element, MX2 type of halides are formed, right? So here M2O when reacts with 2 moles of HX gives 2MX. So like that, metal carbonate gives 2 moles of MX. Here stability, if we consider, stability of fluorides is more than chlorides, then bromides, then iodides. Next, covalent character. So covalent character down the group decreases. Why? Because 1A group elements, if we consider, lithium has more covalent character. Reason is its small size. In the anomalous behavior, we'll discuss again about this. So order, you see, just lithium chloride is more covalent than sodium chloride, potassium chloride, rubidium, then cesium chloride. Same way in second group elements also, from beryllium to barium, covalent character decreases. Means first one, that is BeCl2 in second group, LiCl in 1A group elements are covalent in nature, right? Next, potassium, rubidium and cesium react with more halogens to form polyhalogen compounds. Polyhalogen compounds means what? Compounds in which more than 2 halogens are present, then they are called as polyhalogen compounds. Let us see the example. Potassium iodide reacts with iodine form Ki3. This is a polyhalogen compound. Cesium bromide react with Br2 forms CsBr3. This is also polyhalogen compound. And very important reaction is reaction with liquid ammonia. All the alkali metals react with liquid ammonia, giving a deep blue color solution, right? Here calcium, strontium, barium react with liquid ammonia, whereas beryllium and magnesium, means first 2 elements in second A group, they are not reacting with ammonia. This is because of their high ionization enthalpy values. Okay, so here I have given what the reaction for what metals with ammonia have given. So this here metal is reacting with X plus Y moles of ammonia, then we'll get M plus NH3 taken X plus E minus NH3Y. This is the reaction when metals react with ammonia. So ammoniated solutions are deep blue in color. This is due to ammoniated electrons, so which absorbs red color from visible light, whose complementary color is blue. That is the reason they are having blue color. And next, these ammoniated substances can conduct the electricity. That's why they are conducting in nature, and they are reducing in nature, right? So that you can understand from this equation. O2, when it gains electron, In the presence of ammonia, O2 minus is formed. Again, one more electron is gained, O2 minus 2 is formed. Let us see the anomalous behavior of this lithium. So lithium is behaving differently when you compare with its group elements. So this is due to small size, high positive charge density on the lithium. So it has small size, high electron density is there. That too, positive electron density, positive charge density is there. So that is the reason it has anomalous properties. And at the same time, lithium can form covalent compounds. And ionization enthalpy is high. Electron negativity is also high. And next, hydration enthalpy is also high for lithium. And it is hard and a lighter element. So because of all these properties, lithium is behaving differently from its group elements. Next, let us see. Alkali metals are highly reactive and easily react with air, and generally alkali metals are stored in kerosene. But lithium, if we consider, lithium is stored in paraffin. Why? Because it floats on the kerosene. That is the reason instead of kerosene, paraffin is used to store the what alkali metals, generally that too lithium. So lithium has a high melting and boiling points among the 1A group elements, and the reactivity of lithium, if you see, it is less. And this lithium can form normal oxides, cannot form superoxides and peroxides, but it can form normal oxides. At the same time, it forms nitrites, whereas remaining elements of 1A group, they cannot form the nitrites. So here the properties of this lithium, if you observe, it is different from the rest of the element in the same group. Lithium hydroxide on heating decomposes to Li2O plus H2O. Same way carbonates decomposes to carbon dioxide, nitrates decomposes to nitrogen dioxide, right? Whereas other compounds do not decompose, like NaOH is there, which is also belongs to 1A group only. It is not undergoing decomposition, right? Sodium carbonate also generally it is not undergoing decomposition, but nitrate somewhat they undergo decomposition, forms nitrite, and oxygen is liberated. Now let us see the compounds of the properties of these compounds. Lithium hydrogen carbonate is a liquid in state, whereas other alkali carbonates, if we consider, they are solids. So its lithium properties are different from its remaining element in that same group. Lithium fluoride, lithium oxide, they are less soluble in the water. Lithium chloride is deliquescent in nature. Deliquescent means which absorbs moisture from the atmosphere. That is the reason if you see the compounds of lithium, it is having water of crystallization or hydrated what you call molecules are there in that. And very important thing is lithium shows diagonal relationship with magnesium. That is the reason whatever the properties are shown by magnesium, the same properties are shown by lithium also. Next, anomalous behavior of beryllium also let us discuss. Beryllium belongs to second group element, that is alkaline earth metal. So why beryllium shows anomalous behavior? Same, due to small size, high positive charge density on the beryllium, it shows anomalous behavior. And compounds of beryllium are generally covalent in nature. This is because of what? High electronegativity, high ionization enthalpy, and here this is also having high hydration enthalpy among second group elements, right? And they are harder when you compare with the remaining elements in the same group. Melting and boiling points of beryllium is high, and it is less reactive, dissolves in alkalis and evolve hydrogen gas. Let us see how it evolves hydrogen gas. Beryllium, when reacts with sodium hydroxide, we got sodium berylate, along with that hydrogen gas is liberated. So beryllium oxide reacts to hydroxides of beryllium, forms amphoteric compounds, and it is amphoteric in nature. Beryllium oxide when reacts with acids will get beryllium sulfate. With bases, sodium berylates are formed, right? So beryllium hydroxide when reacts with acid, BeCl2, and NaOH, Na2, BeO2 is formed. That means beryllium has amphoteric in nature. That point here we discussed. So beryllium oxide at the same time BeOH both are having amphoteric in nature. That you can understand by these reactions. And beryllium forms complexes. This is very important point. Why beryllium is forming complexes? First we discussed to form complexes, three important properties it should possess. Okay, what are the three important properties? The size of the atom should be small, right? If size of the atom is small, what happens? It can easily form the what complexes. At the same time, one more, what is another property? Empty orbital should present in that, right? And next, after that, one more is what? Charge also we can consider, right? So these are the very important factors to show complex formation. Diagonal relationship, yes, 1a group, 2a group elements. If we consider first elements in 1a and 2a group, that is lithium and beryllium, shows diagonal relationship. Lithium shows diagonal property with magnesium, beryllium shows diagonal property with aluminium. So these elements has similar size, similar charge or radius ratio, and same electronegativity is there. That's why they are showing the diagonal relationship. Lithium and magnesium both are harder. Lithium and magnesium react with cold water, right? Reacts with cold water, right? Actually here magnesium is not reacting with cold water, it should be hot water, right? Not cold water. There is a small correction in the case of what? Magnesium and lithium. This we can erase. Right. Next, lithium oxide, magnesium oxide, lithium hydroxide, magnesium hydroxide, when heated, right? When they are heated, decompose and forms metal oxides, right? So this lithium and magnesium both forms nitrides like lithium nitride, that is Li3n and Mg3n2. Lithium carbonate, magnesium carbonate both undergoes decomposition and heating, forms metal oxide and carbon dioxide. Lithium chloride and magnesium chloride, so they dissolve in ethanol. And moreover, these two compounds are deliquescent. Deliquescent means, just now we discussed, absorbs moisture from the atmosphere. So they are in the form of hydrated salt, LiCl.2H2O, MgCl2.8H2O. So generally here 2 to 12, any number of water molecules it can form. Next, compounds of that is beryllium and aluminum. If you see, these two also shows diagonal relationship. This is because of same electronegativity of that elements, that is 1.5, and they are not attacked by acids easily due to formation of oxide layer on their surface. So they are not attacked if reacting with the acids. HNO3 when means reacts, it forms NO2 plus H2O, nascent oxygen is formed. Beryllium reacts with this nascent oxygen, forms beryllium oxide. Aluminium reacts with oxygen, form aluminium oxide. Now let us see the structures of BeCl2 and AlCl3. So here you can see bridged chlorine atoms you can see in the structures of BeCl2 and AlCl3. So BeCl2, if you consider, these are the BeCl2, right? So two beryllium atoms are connected with the chlorines. These chlorines are acting as bridges. And here two aluminiums are connected with the chlorines. Means they are acting as bridges. Chlorines are acting as bridges. So generally the common ore of beryllium is called as beryl. Its formula is 3Beo.Al2O3.6SiO2, silica. And next, oxides of both beryllium and aluminium, if you consider, they are amphoteric. That you can understand by following. equations. Beryllium oxide reacts with the acid, same beryllium reacting with base, forms different compounds. A substance which is reacting with both acid and base is said to be amphoteric in nature. Same way aluminum also here, it is reacting with HCl, also reacting with the NaOH, acid and base. So this is also having, both are having amphoteric nature, right? So next, even both aluminum and beryllium can form complexes also, right? So what type of complexes here? BeF2 plus 2F minus gives rise to BeF4 2 minus is given, and BeC2O4 beryllium oxalate type of complex is also formed. Aluminum is also forming complexes like this. Now let us see the important compounds of sodium. The first one is sodium preparation. Let us see by Kastner-Kellner process. In this, the electrolyte is used sodium hydroxide, which on electrolysis will get sodium plus OH minus ions. So generally during electrolysis process at cathode and anode, reduction and oxidation reactions takes place. So in Kastner-Kellner process, cathode is used, iron is used as a cathode, nickel is used as anode. So at cathode reduction takes place, sodium is reduced to sodium atoms. So here Na plus is converted to Na. So this is nothing but what? Reduction. Reduction is taking place at cathode. And at anode, oxidation takes place. 4OH minus is converted to 2H2O, O2, 4 electrons. So in Kastner-Kellner process, very little amount of hydrogen is liberated at anode, right? Next, Downs process. In Downs process, electrolyte used is NaCl, which decomposes to Na plus Cl minus at cathode reduction, anode oxidation. So due to that reduction, Na is released at cathode and chlorine gas is released at anode. Next, caustic soda, sodium hydroxide, which is very, very important and well-known substance in sodium compounds. So here also we are taking brine solution, that is NaCl, which on electrolysis will get Na plus and Cl minus ions. At cathode again same, reduction takes place, sodium ions are liberated, and this sodium is reacted with mercury, Hg, forms amalgam, NaHg. So metal with mercury is called as amalgam. So here metal is sodium, so sodium amalgam we are calling. At anode, oxidation takes place, chloride ions are oxidized to chlorine gas. So whatever the sodium amalgam is formed, that reacts with water, forms sodium hydroxide. So this is the way of preparing sodium hydroxide by which process? Nelson's process, you can say, right? Next, Kastner-Kellner process also we can say. Now formation of amalgam is done to lower down the reactivity of sodium and the rate of reaction is decreases. So that is the reason we are adding mercury to this property. Sodium hydroxide is white solid and is deliquescent in nature, means it absorbs water, and when it reacts with carbon dioxide, carbonates are formed, and it reacts with even amphoteric oxides also, like aluminum oxide, zinc oxide, tin oxide, right, SnO2, next lead oxides, all these are the amphoteric. With amphoteric, this base is reacting, forms different types of compounds. So with aluminum, that is alumina, NaOH is giving sodium aluminate, with zinc, zincate, with the stannum, stannite, stannate, with lead, plumbite, plumbate, right? Even with ZnCl2 also it is reacting and forms hydroxides of zinc. With hydroxides, it is giving soluble hydroxides of Na2ZnOH taken 4. Let us see the uses of this caustic soda. It is used in the manufacture of sodium and it is used as a laboratory reagent. It reacts with the mixture of this calcium oxide and sodium hydroxide is called as soda lime. Next, sodium carbonate. Sodium carbonate is prepared by Salvage process. So in this there are 4 steps are involved. First step is ammonia react with the carbon dioxide and forms ammonium carbonate in presence of water. This ammonium carbonate again reacts with carbon dioxide and H2O, gives ammonium bicarbonate. This ammonium bicarbonate reacts with brine solution or NaCl, gives ammonium chloride and sodium bicarbonate. This sodium bicarbonate on strong heating gives sodium carbonate and released carbon dioxide and H2O. Right? So again, if you want to regenerate the ammonia, simple, ammonium chloride is treated with calcium hydroxide so that ammonia is regenerated. This ammonia again we can use for the production of sodium carbonate by Salvage process. But here the question is, like sodium carbonate, potassium carbonate is not prepared by Salvage process. The reason for this is whatever the K2CO3 is released, right, it can be converted to KHCO3, right, and this KHCO3 is soluble in water. If it is soluble, it is not suitable to prepare potassium carbonate. Properties: it is a white crystalline solid. On heating, it loses 9 water molecules and converted to natrum or monohydrated sodium carbonate. Further heating loses that one molecule also, that is one molecule of water, and forms soda ash, sodium carbonate, sodium bicarbonate. So sodium bicarbonate is also called as baking soda. Baking soda, whereas sodium carbonate is called as washing soda. Right? Now let us see. So here same, sodium bicarbonate is also prepared from Salvage process. First 3 steps if you observe, ammonia with H2O, CO2, ammonium carbonate is formed. Next, carbonate again reacts with CO2, H2O, forms bicarbonate. Bicarbonate treated with NaCl will get sodium bicarbonate. So it is a white crystalline solid, sparingly soluble in water, and it is stored. It is not stored with strong bases. Why? Because if it is stored with strong bases, it is forming the carbonates, right, which are undergoing decomposition easily. That is the reason it is not stored with strong bases. So itself it is undergoing decomposition and heating forms sodium carbonate, carbon dioxide and H2O molecules. Let us see compounds of calcium also. First one is calcium oxide. So generally calcium oxide is produced when calcium carbonate is heated. The properties of this, if you see, when it is calcium oxide is reacting with water, will get slake lime, calcium hydroxide. So at the same time, some heat energy is released out. When calcium oxide is heated, right, oxyhydrogen flame is formed, then white light is produced. So this is called as lime light. So calcium oxide, when treated with carbon, calcium carbonates or carbides are formed. That calcium carbide treated with water will get calcium hydroxide. Even calcium carbide react with nitrogen also forms calcium cyanides. So this calcium hydroxides are used in the purification of sugar and in the preparation of slag in metallurgy process. We are using this. So basic flux, calcium oxide is a basic flux. To this acidic impurity is added. Next, slake lime. So slake lime, if you see, calcium hydroxide. Slake lime is nothing but what? Calcium hydroxide. So that is prepared when calcium oxide is treated with H2O, CaOH taken twice 2 is formed, along with that heat energy is released. Calcium hydroxide treated with carbon dioxide, calcium carbonate is formed, and this calcium bicarbonate on heating also we can get calcium carbonate, H2O, CO2, and it is used in whitewash and the preparation of bleaching powder and the glass, in the purification of sugars and the removal of temporary hardness of water, right? We are using this compound, calcium carbonate. So calcium hydroxide, when treated with carbon dioxide, calcium carbonate is formed. When calcium chloride is treated with sodium carbonate, calcium carbonate is formed, and it is white crystalline substance, insoluble in water, and it is decomposes to calcium oxide and carbon dioxide. Its uses are: it is used in the construction of buildings, as a basic flux in metallurgy, and used in toothpastes. Let us see cement. Cement is a mixture of calcium oxide, silica, aluminum oxide, magnesium oxide, iron oxide, sulfur trioxide. So the composition is, that is quicklime is 50 to 60 percentage, silica is 20 to 25 percentage, aluminum oxide is 5 to 10, magnesium oxide is 2 to 3 percentage, iron is 1 to 2, and sulfur trioxide is 1 to 2. So maximum percentage is quicklime. And in this, silica and Al2O3 is 4:1 ratio, we can say. Calcium oxide and other are what? 2:1 percentage it is there. Next, Portland cement. Portland cement composition, if you see, calcium oxide is 61.5, silica is 22.5, alumina is 7.5, magnesium oxide is 2.5. Now let us see important ingredients of Portland cement. Dicalcium silicate, tricalcium silicate, tricalcium aluminate, tetracalcium aluminate ferrite are the important ingredients in the Portland cement. So gypsum is added in cement to slow down the setting of cement. That is the importance of gypsum. So here calcium sulfate of 2 moles of H2, that is what? CaSO4 dot 2H2O on heating loses water molecules and gives CaSO4 dot half H2O, plaster of Paris is formed, and we'll get dead burnt plaster is formed. Biological importance of these elements, let us discuss. KO2 is used in space capsules, submarines, because to remove carbon dioxide and gives oxygen. This is the reaction. Calcium chloride is used as drying agent because it is hygroscopic in nature. Anhydrous magnesium, that is nothing but perchlorate, is used as dehydrating agent. Next, electron alloys, 95% of Mg, 5% of zinc, right, is called as electron alloy, which is used in making of aircraft bodies. Sodium and potassium controls blood pressure of human body, and also potassium is used in the conversion of glucose into ATP and ADP. So these are the important concepts related to S-black elements. Thank you.